In this recording, we will discuss propagation of action potentials. So we've discussed how to make an action potential. Now we're going to talk about how to propagate or conduct an action potential. So remember, an action potential has to travel down the entire length of an axon, which is kind of a long distance. The action potentials themselves are self-propagating, and they only travel in one direction. This occurs from the axon hillock towards the axon terminals. Okay? And we accomplish this by opening up successive sodium ion channels as we go down the length of the axons. Okay? Each subsequent sodium ion channel that we have opened, don't forget, eventually it will inactivate and eventually go back to rest during that refractory period as the next section of axon depolarizes. Okay? As the action potential propagates down the axon, we term this a nerve impulse. Okay, so just kind of a nice keyword to keep in mind, nerve impulse. All right, so here's kind of what it looks like. We've got our little section of axolemma. Okay, so axolemma. Now, we're going to start on the left. Okay. You can see we are depolarizing this first section of axolemma. Okay, and we're going to come to our first voltage-gated sodium channel. You'll see right here that triggers the depolarization by opening this first voltage-gated sodium channel, and you can see this next section of axolemma also becomes depolarized. And look who is sitting right next to this section. Ooh, look at it. It is another voltage-gated sodium channel. So we activate, we open this sodium channel, more sodium rushes in, which depolarizes this next section. Ooh, look who we're coming to, y'all. We got a third voltage-gated sodium channel. Again, that depolarization is going to open that channel, more sodium ions rush in, and we just continue going down the line. Now that we pay attention to our sodium channels, okay, let's make sure we understand what else is happening. Okay, so after we have opened our initial sodium channel, we activated our initial sodium channel, we depolarized this section of membrane. Okay, once we open that next sodium channel, okay, once we start depolarizing the next section of axolemma, what happens to our first section? It starts repolarizing. Okay, so you'll notice that we have inactivated this original sodium channel, and we have activated or opened our first potassium channel. So you'll notice that our membrane potential is starting to go back to resting membrane potential. Okay, and same thing for our next section. So once we finish depolarizing section number 2, and we pass the signal off to section number 3, section number 2 starts to repolarize. Okay, you'll notice in section number 1 we have completely gone back to rest for our first sodium channel. Our second sodium channel becomes inactivated. Our first potassium channel is now back at rest. Our second one has been activated, so now we repolarize section number 2. Once section number 3 finishes depolarization, it would also start repolarization. Okay, so we're just kind of going down the line. Okay. The rate of propagation, or the conduction speed of an axon, is determined by two things. First thing is the diameter of the axon, and the second is the presence or absence of myelin. Okay. So the larger the diameter of an axon, the faster it can conduct the action potentials. Because the larger the axon, the lower the resistance, okay, to the conduction. Resistance is kind of what it sounds like. You are trying to resist a change, but the larger your axon, the lower resistance, so the easier it is to conduct those action potentials. Now, the presence or absence of myelin really causes how we propagate the action potential to change, because we have two types of conduction. We have saltatory conduction and we have continuous conduction. Now, saltatory and continuous conduction, let's show some examples. Okay, so saltatory conduction, this is how myelinated axons work. Okay, so remember myelinated axons in the central nervous system, we're talking about myelin coming from the oligodendrocytes. In the peripheral nervous system, we're talking about myelin coming from the Schwann cells. All of it really has to do with those, the plasma membrane of those cells wrapping around the axon and insulating them. So, if you remember back to what that looked like, we pointed out internodes and nodes of Ranvier. Okay, so not every single little section of axolemma is insulated or myelinated. Okay, you have bare sections. Those are the nodes of Ranvier. Okay, the blue sections, the myelinated sections, those are your internodes. Okay, so here's how this works. In myelinated axons, okay, where you have the myelin sheath itself increases the efficiency and the speed of conduction, okay, and the action potentials only depolarize the nodes of Ranvier and they jump over internodes, which is kind of cool. So here's what it looks like. Okay, so we're going to go left to right. So, first step, we start our action potential. You know that that involves depolarization of the voltage-gated sodium channel. Okay? Notice where our sodium channel is. It is in a node of Ranvier. Okay, you don't see any sodium channels in your internodes. Okay, so we have started our action potential. Okay. We are going to send this action potential down the line. All of these little positives are going to become negatives. They're going to depolarize. Okay? You're going to make it all the way to the next node of Ranvier where you find your next voltage-gated sodium channel, which causes depolarization, and it spreads through the internode, and we do it for a third time. Okay? So, the change in membrane potential you see in the internodes, okay, makes its way to the next node, to the next node, to the next node. The internodes, okay, are just wide enough to where we receive the action potential, okay, from one node to the next. Now, let's see how that compares to continuous conduction. So continuous conduction is how unmyelinated axons work, which means you have to depolarize every single little section. Boop. Okay. Every section of axolemma, okay, from the trigger zone, the original depolarization zone, all the way to the axon terminal, you must propagate the action potential down the entire length. You don't get to skip over anything, okay? Because that was the main point in our last picture. You basically get to skip over, boop, 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 the internodes. Well, there are no internodes here. We don't get to skip anything, okay? So once we start depolarization, we have to do every single little section, okay? You'll see every single, we're still going, woo, still going, boop. Okay, let's see how this actually gets us anything. All right, so on the top we have saltatory conduction. On the bottom we have continuous conduction. Okay, so we're starting at the same time in the same place. Okay, on the top we are depolarizing in our node of Ranvier, and we get to skip over to the next node. Okay. Here's our next node, and then we get to skip over to our third node. Okay, remember we're skipping over these whole sections of internode. Okay, down here we don't get to do that. All right, we have to depolarize every single section. Okay, gonna have a lot more sodium channels, and by the time our action potential at the top reaches the terminal, we're only about 75% of the way done with the continuous conduction. Okay, so getting to skip over these internodes lets our conduction go faster. Now, multiple sclerosis. This is an autoimmune disorder that attacks the myelin sheaths within the central nervous system itself. Okay, so remember, your central nervous system is your brain and your spinal cord. Okay. This causes the progressive loss of myelin because your body is attacking itself. Okay. This in turn causes the loss of conduction from one neuron to the next. Okay, so you are basically losing the signal in these damaged areas. Okay, we don't want that, because if they get lost, they don't end up where they need to go. Some symptoms include progressive loss of action potentials, or the slowing down of the action potentials. The central nervous system. Okay. Again, the brain, the spinal cord. This is where you start voluntary muscle contraction. Okay, so you tend to lose. Okay, you have motor dysfunction, including paralysis, and then sensation is also processed here. And so if you lose that ability, you'll experience a lot of numbness. This can even alter certain behaviors. You can lose cognitive abilities, things like that. There are treatments for multiple sclerosis, or MS, but as of right now, there are no cures.